Hi, welcome back to Statistics 1. We're up to Lecture 10, and the topic in Lecture 10 is confidence intervals. Last week we talked a lot about null hypothesis significance testing, and we talked about some of the problems inherent in NHST and a lot of the criticisms of the entire approach of NHST. So in this lecture we'll talk about an entirely different approach, which is just to report confidence intervals around sample statistics rather than engage in inferential statistics per se. Let me explain what I mean. So in this lecture, I'll divide the topic of confidence intervals for now into just two segments. In the first segment, I'll talk about confidence intervals around sample means, and then hopefully reinforce the idea of confidence intervals by talking about confidence intervals around regression coefficients, since we've spent a good bit of time on regression, and again in the next lecture we'll be talking about multiple regression. So this should be fresh in your minds at this point. So let's launch into the first segment. Here we'll just talk about confidence intervals around sample means. This is sort of the easiest and most obvious place to start when talking about confidence intervals. Now, what do I mean by a confidence interval? Well, remember that all sample statistics, be it a mean, a correlation, a regression coefficient, whatever sample statistic we take, are simply what statisticians would call point estimates. That is, they're just one point in an entire possible sampling distribution. Remember the whole idea of sampling error and sampling distributions and the concept of the central limit theorem? What that implies is any one sample will never be perfect if we're only getting a random sample from a population. So the statistical phrase for that is we can only get a point estimate from a sample. So if we think about sampling distributions, remember this was the family of t distributions. These are all sampling distributions. They vary slightly, remember, due to sample size. So these degrees of freedom, that's just n minus 1 in the simplest case. So you can think of that as sample size. But each of these are sampling distributions. And when we get a sample mean from a distribution, we just fall somewhere in that sampling distribution. We're one point in that sampling distribution. That's the point of a sample mean or any sample statistic. It's just one point in this entire possible range of values, this entire distribution. So the logic of confidence intervals, which statisticians really approve of, a statistician would recommend always report your confidence intervals. Those of us who are more applied, we tend not to do it, and you'll see one of the reasons why is they're so wide. One author called them embarrassingly large. The point estimates just seem more accurate, but that's an illusion. So again, the logic of the confidence intervals is to report a range of values rather than just a single value. So rather than just report the sample mean, report a range, a possible range of values. And we'll call that an interval estimate rather than a point estimate. So to be clear, a confidence interval is an interval estimate of a population parameter based on one random sample. The degree of confidence, like how confident we want to be in this interval, for example, 95%, that's one of the most common confidence intervals that's reported. When we do this in lab and we do this in the R software, that's the default confidence interval is 95%. That represents the probability that the interval will capture the true population parameter. Okay, so this is the formal definition of confidence interval. And again, the main argument for interval estimates is the reality of sampling error. We know that we have sampling error, so let's just be upfront about that. If we're just reporting a point estimate, then we could be fooling ourselves. Worse yet, we could be fooling our audience, our readers. So why not report an interval and just acknowledge the fact that we have sampling error? Sampling error, remember, implies that every point estimate, any one point estimate, is going to be off to some degree. How much is it going to be off? Well, that has to do with how much sampling error we can expect, and that we estimate, remember, with standard error. So the bottom line here, this is where the phrase confidence interval comes from, is researchers will be more confident, or should be more confident, in the accuracy of what they're reporting if they report an interval estimate rather than a point estimate. So let's get back to the specific topic of confidence intervals for a sample mean. And again, I'm going to use the example of the impact data. We've used these a few times, so I thought I would use this again to illustrate confidence intervals. Let's assume we took just random samples of only 30 athletes from those impact data. Remember, we had more than that, but let's assume we just took random samples of 30, and we repeated that random sampling process, and we would get a sampling distribution, right? We don't actually do that, we just get one sample. But let's assume we did it multiple times. Here I'm just showing you, actually I did it to prepare this lecture. I did it in R, I just randomly sampled samples of 30, and I got the symptom score at baseline. Remember, symptom score at baseline should be 0 because these are healthy athletes. Not everybody is at 0. Some athletes come in at baseline and they might reveal some symptoms. So the mean isn't exactly 0. And if I get repeated random samples of size 30, then the mean's not going to be exactly the same each time because of sampling error. So the first time I did it, I got a mean of 0.05, then I got 0.07, then I got 0.03. So it's close to 0. There's not a lot of fluctuation because my sample size is not bad, considering there's not much variance in this variable at baseline. Now let's decrease the sample size to 10 and do it again. So now I decrease the sample size to 10, I get symptom score at baseline. Again, the mean is going to be near 0 because these athletes are healthy. But notice I got 0.01, I got a 0.2 in there, and a 0.00. So now there's more fluctuation in my point estimates, in my sample means, as I do that over and over again. Now let's look at symptom score post-injury. Now the mean shouldn't be 0 anymore because these athletes have been concussed. They're going to show a lot of symptoms. So first, let's do it again with n equals 30. I get a few random samples. I got a mean of 12.03, then I got a mean of 12.9, then I got a mean of 14.13. So a little bit of fluctuation. Again, that's just due to chance. That's sampling error. But let's decrease our n to 10 and do it again. Now these are athletes post-injury, but smaller sample, random samples of 10. I got 19.7, then only 8, and then 13.3. So again, you get more fluctuation with the lower n because there's more sampling error when we have a smaller sample size. The other thing to notice is we get more fluctuation in the post-injury scores than in the baseline scores because there's more variability post-injury, right? So the point of that little exercise is the width of a confidence interval is going to depend on two things. Sample size. So as sample size goes up, the width of the interval is going to get tighter because I'm going to be more confident about my estimate, right? The other thing that will influence the width is the variance in the population, and therefore the variance in the sample if we're getting a random representative sample from the population. So more variability in the sample means more variability or a wider width in that confidence interval. All that is to say is standard error is going to drive the width of the confidence interval because remember, standard error is the standard deviation of the sample over the square root of n. Remember, that's where if we could jack up n and get really big samples, then we get really little standard error, because standard error is how much sampling error would I expect just due to chance on average. That's standard error. So I ran this in R, and you'll be doing this in lab. So with the sample size of 30 and using symptom score as my variable, the 95% confidence interval at baseline was negative 0.03 to just 0.1. So right around 0. Notice it goes below 0, which doesn't make any sense. That's not a possible score on the symptom score. But what it does is, you'll see the calculation in a moment, it just calculates the mean of the sample times standard error and times some function of standard error. So it might go below 0 if the true score is 0. But notice how tight that is. It's not a very wide interval. I have 95% confidence that the true score is somewhere in there, and it should be. The true score should be 0 or very close to 0, because these are healthy athletes. They're taking this at baseline. So it's right around 0. It's a very tight interval. If I go down to a sample size of 10, again, I just ran this in R to see what I would get. Now I'm going a little bit even further below 0, which is weird. But now I'm up to 0.5. Again, it's right around 0. That's because there's not much variability in this variable at baseline. But you see how the width of the confidence interval gets wider as sample size goes down. That's because we have more standard error when sample size is lower. Now this is more interesting. Let's look at symptom score after the injury. Again, let's start with a sample size of 30. Again, I just ran it in R with a random sample of 30. And here's my 95% confidence interval. It's 7.5 to 18.3. So that's a pretty wide range. And I have a sample size of 30. It seemed much more accurate before, right? When we just reported the point estimate. When we just said, well, the average symptom score is, say, 12. You know, then that would be, I could walk away and say, all right, well, this is how serious the injury is. They have about a 12 on the symptom score. But again, that's a point estimate just from one sample, and there's some degree of sampling error associated with any one individual sample. So it would be more honest and more accurate, and I could be more confident in my reporting if I reported this interval estimate rather than a point estimate. But I would have to show just how wide the interval is. And here it's 7.5 to 18.3. It gets worse as sample size goes down, of course. So now let's look at it with an n of 10. Now let's look at the 95% confidence interval. 2.7 to 23.9. It's basically saying with an n of 10, I don't know where you're going to fall on this thing. 2.7 is close to 0. That's close to showing no symptoms at all. And 23.9 is almost off the charts on this scale. So with a sample size of 10, if you want 95% confidence that you're capturing the true population parameter, you're going to have to report a really wide interval. And again, this is why I think most researchers don't actually do 95% confidence intervals, because as I said, this one author called them embarrassingly large. This is a good example of one that's embarrassingly large. So how did R actually calculate those confidence intervals? Where it should be sort of intuitive to you by now that what we do is just take the sample mean, because remember, we only have one actual sample. We take that sample mean, and to get the upper bound of the interval, we're going to add standard error, because as standard error goes up, we want to increase the width of it. But we want to multiply that by a t-value, which we get from the t-distribution. And then to get the lower bound, we do the same thing, except we subtract t times standard error, where standard error is still just standard deviation of the sample over the square root of n. This t statistic, it just depends on the level of confidence desired. So for now, let's stick with 95% confidence intervals. And that corresponds to an alpha of 0.05, that idea of you need p less than 0.05 to reject the null hypothesis. That's why 95% confidence intervals are sort of the standard, because alpha of 0.05 is also the standard. So the t, the actual t value that gets plugged into this formula, depends on the level of confidence desired, say 95%, and sample size. Why sample size? Well, because again, the sampling distribution that we assume depends on the exact size of your sample, where the width of the sampling distribution gets a little bit wider with smaller samples, right? Smaller samples are going to give me more standard error. So if I want 95% of that distribution, then I'm going to have to go a little bit further out. I'm going to need a slightly higher t value. So that's why it depends on both standard error and the t value. So to wrap up this segment, remember that all sample statistics, and this is a critical thing to remember as a consumer of statistics, that any one sample is just a point estimate. And now that we know about this idea of sampling error, we know that there exists out there in the world this hypothetical idea of a sampling distribution. So you should know that any one sample is just a point estimate in that possible sampling distribution. So this any one sample mean is just represents 1 point in a larger distribution. So the logic of confidence intervals is to report a range of values rather than just a single value. And in statistics, that's called reporting an interval estimate rather than a point estimate. And perhaps most importantly, just know that the width of the confidence interval, what influences that? Well, standard error. And what influences standard error? Sample size and variance in the population. And that hopefully now conceptually rings true to you, but also mathematically should make sense to you, because we've dealt with this formula a few times now. So standard error is standard deviation over the square root of n. So as variance in the population goes up, standard deviation in my sample should go up if I'm getting a good estimate. So if standard deviation goes up, standard error goes up. And as I've said repeatedly now, if sample size goes up, then the denominator of standard error goes up, standard error is going to go down. Okay, so the width is going to depend on those two elements, and put together just standard error.